This is Pre-Calculus section 2.7 notes. Hello math friends. Today we are going to be talking about combinations of functions. In order to define these combinations, we're going to have our two functions, f of x that has a domain of a and g of x that has a domain of b. Because whenever we talk about operations on functions, we always have to be cognizant of their domains and what the domain of the combination will be. So the first thing we could do is we could add our two functions f and g together. So f plus g of x really just means that we are taking f of x and we are adding it to g of x. And if you think about that, you can only add two functions together in the places where both functions live. And if you can only do it where both functions live, then their domain has to be the intersection of the domain of A with the domain of B, because that would be where they overlap or where both functions exist. The difference of two functions would be f minus g of x, or f of x minus g of x. And just like addition, the domain is going to be the same. You can only add them together where they both exist. The product of two functions, f times g of x, is f of x times g of x. And again, same rules apply for the domain. You can only multiply them together where they both exist. And then finally, we have the quotient of two functions. So f divided by g of x, which is often written as f of x over g of x. Now this one has a little extra caveat to it because we're talking about a fraction which has a denominator. I'm sure you can see what's coming here. We would say our domain has to be that all of our x values have to live in the intersection of a and b, but also our function g of x cannot equal 0. And we say that just so that we can prevent our denominator from becoming undefined. So let's do a real problem example. F of x is the function 1 divided by x minus 4, that's a family, and g of x is the function the square root of x. So if we consider these two functions individually, if we look at the first one, the domain for that function, we do have that family x minus 4 in the denominator. So the domain of f of x would be that x cannot equal 4. Because that would be the one number that would make our denominator 0, and we cannot have that. So right below here on that first dashed line, I'm going to graph what my domain of A looks like. So basically, I've got the number 4, which I know my function is not allowed to be. So I'm going to put an open circle there, but it can be anything else. So I'm going to shade to positive infinity on the right, and I'm going to shade to negative infinity on the left. Now, the domain of g of x, we're going to call that b. G of x is the square root of x. And we know that for the square root of x, all of our x values, anything under the radical must stay 0 or bigger. So we're going to say our domain is that x must be greater than or equal to 0. And we're going to graph the domain of b on the bottom dashed line. So here would be the number 0, and 0 is included because we can have 0 under the radical. We just can't have anything less than 0. So anything 0 and up is going to be good for our domain for our g of x function. And so now we're looking for, well, for our domain, what would be that intersection of A and B? So graphically speaking, our intersection is where do these two overlap? Well, if we start on the left-hand side, we can include the point 0, but we can't include anything less than 0 because both of them have 0, but then g of x does not include anything below 0. We can't include 4, so we have to have an open circle at 4, but then beyond 4, both of them go to positive infinity. So we've got this area filled in between 0 and 4 with a hole at 4, and then we go to positive infinity. So we would say that the intersection of A and B would be that x has to be greater than or equal to 0 and x cannot equal 4. If we wanted to write that as an interval, then we would say our first chunk there of our number line includes 0, but doesn't include 4. And then our second interval doesn't include 4 and goes up to positive infinity. So that's how we would write that in interval notation. So now that we know the domain of A, or the domain B, the domain A, and we know what the intersection looks like, now we can do a little bit of algebraic work with our two functions. We can do some combinations with these two functions. So our first combination is going to be f plus g. And just a little reminder up here, my domain here is that x cannot equal 4. My domain here is that x must be greater than or equal to 0. So if I want to add f of x plus g of x, that's just going to be 1 over x minus 4 plus the square root of x. I cannot combine that any better. Those aren't like terms. I've got a radical. I've got something that's not a radical. I suppose I could find a common denominator and add them together, but at this point, I'm just going to leave it like that. And my domain is going to be the domain that I found on my previous page. It's going to be the intersection of the domains of f and g, which is x has to be greater than or equal to 0, and x cannot be 4. F minus g is going to look very similar. You're going to have 1 over x minus 4 minus the square root of x. Again, I'm not going to worry about creating a common denominator and simplifying that further. You certainly could. Your common denominator would be x minus 4, and then you'd have to multiply the square root of x by the family x minus 4, so we could certainly combine them here. But again, our domain is going to be x must stay greater than or equal to 0, and x cannot equal 4. F times g is going to be 1 over x minus 4 times the square root of x. So this I could clean up a bit, and I could just put the square root of x in the numerator and x minus 4 in the denominator. And again, as stated on the previous page, my domain is going to be x must be greater than or equal to 0. X cannot be 4. And then finally, we have f divided by g, or f over g. So this is going to be 1 over x minus 4 divided by the square root of x. Now, when you divide fractions, remember you are doing keep, switch, flip. So this really becomes 1 over x minus 4 times 1 over the square root of x, which would give me 1 over square root of x times the family x minus 4. So that's all in the denominator. So this changes our domain a little bit here. So I'm going to put a star here. X can no longer be 0, because now if you look in the denominator, we have that square root of x in the denominator. So we can't say x must be greater than or equal to 0 and x cannot equal 4. Now we have to say x must be greater than 0 and x cannot equal 4. So notice we had to change that inequality symbol. We can no longer allow x to equal 0 because when we did division, that square root of x ended up downstairs. Our next example here allows us to kind of give an actual graphical representation of what it would look like if we added the functions f plus g. So we've got these pictures on our graph, and I'm going to kind of color code this for you so that you can see what we're doing here. I'm going to start with f of x. So if I were to go ahead, I'm going to use this color red, kind of this orangish red here. It's a pretty good match. If I were to go ahead and identify what are all of the y values on f of x when x equals these numbers, I would just be looking at the graph and estimating them, because obviously they're not all perfect ordered pairs. So the numbers that I'm writing here in the f of x columns are just my estimations of what the y values are on that orange function when x is -3, and then when x is -2.5, it's positive 0.5. When x is -2, the function's at 0. When x is -1.5, my function is at -0.5. When x is -1, the function is at -1. When x is 0, the function's at about 0.3. When x is 1, the function's at about 0.1. When x is 2, the function is at -0.5. And when x is 3, the function is at -1. All right, so now I'm going to do the exact same thing with my g of x function. The first thing that I'm going to do here is I'm just going to identify what are my y values for these x values in the table when I look at that function. So when x is -3, it's really important to note that the g of x function doesn't exist there. And obviously, in order to be able to add them together, that should say DNE, looks like ONE, does not exist, DNE. In order to be able to add them together, both functions have to live there. So since g of x doesn't live there, I'm not going to be able to do that addition. And the same thing here when x is -2.5, that blue function doesn't live there, okay? The blue function really doesn't start until x is -2, and then the blue function has a value of +1. And then I can continue on from there. When x is -1.5, the blue function's at about 2.3. When x is at -1, the blue function is at about 2.25, 2.25 looks like. When x is 0, the blue function is at 1.5. When x is 1, we're at about 2.5. When x is 2, again, we're at 2.5. And then when x is 3, we're at about +1. Okay, so now we get to add together our f function plus our g function. So obviously, if one of them does not exist, then the addition of the two functions does not exist. So the addition of my functions will not exist before x is -2. But now when I do this graphical addition, I'm just going to add the value of f of x and the value of g of x. So this is going to be +1. This is going to be +1.8. When x is -1, my addition is going to be +1.25. When x is 0, it's going to be +1.8. When x is 1, it's going to be +2.6. When x is 2, +2. And when x is 3, it's going to be at 0. So now I'm going to go ahead and I'm going to plot these values. Okay, so when x is -2, my function is going to be at 1. When x is -1.5, it's going to be at about 1.8. When x is -1, it's going to be at 1.25. When x is 0, it's going to be at 1.8. So up there. When x is, sorry. When x is 1, we're going to be at 2.6, right there, a little above the blue line. When x is 2, we're going to be at 2. And when x is 3, we are going to be at 0. So the graphical addition here, if I go ahead and kind of draw this line, oops, this point right here is out of place. I apologize. That should be at about 1.8. That should be up there. Apologize for that. So now if I go ahead and connect this, the graphical addition of my functions looks something like that. A little bit funky, but that's exactly how you do it.